We've been talking in this section about measures of center for data sets, and we've talked a little bit in previous lessons about measures of relative standing with percentiles and quartiles. Let's discuss a specific type of measure of relative standing that will allow us to compare one data value, so maybe your particular test score, with that of the average or the mean of the rest of the test scores. So let's look at this example. SAT scores and ACT scores, both are really similar in students sit down, they take a long test, and they get a score when they're done, and they're used in college applications. But their values are very, very, very different. SAT scores have values, for example, with a mean of 1,518 or a 1518 on the SAT is the mean, and standard deviation of 325. ACT scores are a lot smaller in number. ACT test scores have a mean of 21.1 and a standard deviation of 4.8. So if you are applying to a college, which has a relatively better score, a 1030 on the SAT or a 14.0 on the ACT? One of the things that we're going to talk about in this section will help us compare those two scores, the 1030 compared to the 14.0. What we're going to talk about in this section is a z-score. And what a z-score is a z-score is for any data value, it tells you how many standard deviations that value is above or below the mean. So if your particular test score is much, much better, it might be 1.5 standard deviations above the mean or above the average. In other words, you would have a z-score of 1.5. Or if your z-score is just a little bit below the average, so your test score is just a little bit below the average, you might have a z-score of negative 0.5. If you have the mean or the average of a data set and the standard deviation, you can calculate the z-score. We have similar formulas for a sample z-score and a population z-score. For the sample z-score, you take the data value that you want, subtract from it the mean, so the data value minus x bar, minus the mean, and divide by the standard deviation of the sample. The formula for the z-score given a population is exactly the same. We just use mu, that mean for the entire population, and lowercase sigma, that s, for the standard deviation of that population. But the formula is the same. Okay, so let's practice an example with just 5 data points here. So let's calculate the z-score for the number 10 in the following set of data: 12, 15, 16, 10, and 9. Now there are 2 calculations that you should pause this video and try to do on your own. One is the mean. So adding up all the values and dividing by the total number, which is 5. The mean for this is 12.4. The other value that we're going to need for the z-score is the standard deviation. That one's a little bit trickier. We covered in the previous lesson. You can use either the original formula or that shortcut formula to find the standard deviation. But when you calculate that, you should get a standard deviation of 3.05. So if we're going to find the z-score for the value 10 in this data set, we're going to calculate that number, 10, minus the mean, minus 12.4, divided by the standard deviation of 3.05. And when we do that, we get a z-score of negative 0.79. So what that means is the score of 10, or the number 10, is 0.79 standard deviations below the mean. It's 0.79 standard deviations below the mean of the data. One use of z-scores is that they let us compare values that otherwise would be difficult to compare accurately. So going back to that example of an SAT score compared to an ACT score, let's compare if we know the mean of the SAT and the standard deviation of the SAT, and we know the mean of the ACT and the standard deviation of the ACT, we can compare a student's score on the SAT of 1030 with his or her score on the ACT of 14.0. So let's find the z-score for the 1030 on the SAT. So we would do the data point, 1030, minus the mean, so minus 1580, and then divided by the standard deviation of 325. And we get negative 1.5. So this student's score is 1.5 standard deviations below the mean. If we do the same thing with the ACT score, the student's score was a 14.0, and subtract from that the ACT's mean of 21.1, and dividing that by the ACT standard deviation of 4.8, we'll now get a z-score for the ACT of negative 1.48. So the ACT score, a little bit higher and a little bit closer to the mean, this ACT score is a better score than the SAT score. So really helpful to be able to compare two scores that have a totally different number system. We've talked in the past about usual and unusual values, and I want to translate that into z-scores. Unusual values have z-scores that are within 2 standard deviations of the mean. So the z-score is within -2 and +2. Unusual values have z-scores that are greater than 2 or less than -2. So a usual value would be a z-score in between -2 and 2, and an unusual value would be a z-score of like 3 or maybe -7. Those would be unusual values. So for example, if we're looking at this data set, say we have the data values 239 and 237 and 242 and 5, 238 and 240, which of the following probably has a z-score less than -2? Probably the 5. That is a very unusual, unexpected value in this data set. And on the other hand, if we have the data 20, 23, 19, 1,239, 15, and 3, then the value that probably has a z-score associated with it that's greater than 2 is the 1,239. It is much, much, much bigger than all the other data given. So z-scores are really helpful in determining usual and unusual.